Okay, so the recorder is on at this point in time. I'm going to go ahead and share my screen with you guys. Please let me know if you guys can see it. Just a quick little message through the chat will be good enough for me to let me know that you guys can see my chat window. You guys can see my desktop, okay? So let me know if that's the case. Okay, cool. Good. Thanks, guys. So I got a few responses letting me know that they can see it. So I want to start off talking a little bit about modeling in general. This was something that was pretty lacking in the last demonstration that I made, and from comments that I've received from users, I noticed that it's good to clarify a few points about simulation. A lot of new users, especially those that are maybe starting off in their college careers in electronics, they look at simulation almost like a virtual playground, you know, that it's going to mirror reality, that if it works in the simulator, it should work in real life. There's a few caveats to that, and I kind of want to discuss that a little bit. Here I have a quick little article about the models that are used to simulate op amps, and something that I want you guys to see is specifically this picture. Okay, if you've ever looked at a data sheet of an LM741 or any other op amp, usually the data sheet shows you the real schematic, the internal schematic of the op amp, and you'll notice that it's pretty much lots of transistors, lots of resistors, and maybe a couple of caps and a few diodes, and that's about it. That's not what you're seeing here, okay, as you guys can tell. The reason we model and the reason we simulate is that usually we don't need a super exact answer. You know, an answer that's within 1%, you know, is more than good enough. And with the quality of simulations today, you can actually get much better than that. But if you had to simulate, if you had to calculate all of the node equations for all of those transistors in that LM741 schematic, as you can see in a data sheet, for example, the amount of time it would take is just not practical. So we simplify. We model the behaviors of the components using, you know, parts like you can see here, a few resistances, we have a current source, we have a few voltage sources in here, okay, so on and so forth. And these models are valid within a certain range, within a certain set of parameters and characteristics, okay? If the design you make, whether you know it or not, is outside of the realm of applicability, then the results you're going to get through the simulator are garbage, okay? So keep that in mind. The reason we simulate and the reason we model is to simplify and to get intuitive understanding of the circuits that we're working with. That's why here you can see that it's not the exact model of an internal op amp. Here we see another type of model, okay, and again, no transistors here, nothing like that, with the exception of the JFETs here at the beginning, which are used to model the input stage. Again, we have circuit symbols like the ones we learned in circuits class of current sources, voltage sources, okay, which in real life are not ideal, number one, and it's not as simple as just making a little symbol for it. You know, power supplies have circuitry dedicated strictly to themselves and can be quite complex. So as you can see, this model is also a simplification of reality. So we want to keep that in mind. The realm of applicability of the models that we're working with. What are the limitations? Usually manufacturers will specify the models for what they're good for. For example, in power supplies, you can have steady-state models, which allow you to simulate the behavior after all the transients have died down and the power supply is working with a steady load. And we also have transient models that model the behavior when the power supply is just starting up, and you have all of these little, you know, power-up issues such as, you know, the capacitors charging on the input, so on and so forth, which are neglected in the steady-state models. So don't look at the simulator as the ultimate source of truth when you're designing your circuits. A lot of students will not think about the circuits. They'll just draw it out in the simulator and just try to simulate and simulate and simulate until they get something that works. That's not the best use of simulation. the late Bob Pease always used to really bash people who relied on SPICE simulators. He knew how to use them, and from the evidence that's been recorded, he apparently knew how to use them very well. But he understood their limitations, and he understood that in order to make the best use of it, the simulator needed to be a sanity check. He needed to have some idea of the output he was expecting. That's something we're going to see as we go on through our discussion. Okay, the first thing I want to point out now is resources. Okay, besides this video, where can you find information about LTSpice, information about EAGLE, so on and so forth? So that's where I'm going to start. Okay, so first and foremost, for LTSpice, which I have open here, in the Help menu, the topics, there's a wealth of information. If you go to the frequently asked questions, you're going to notice a lot of important sections that may be of interest. For example, how to simulate transformers in SPICE. What are the limitations of these simulations of these models? How to use third-party models, which is what we're going to be doing today. Various inductor models, MOSFET models. How to do custom symbols, very important. Generating Bode plots, etc. Okay, so make liberal use. Whenever you have a question about LTSpice, this is the first place to go. Okay, and it's very comprehensive, covers all the elements that come with LTSpice, all of the standard syntax, different things that can be done, what equations govern them. Very, very comprehensive. Okay, so any questions about LTSpice, this is a great source to go to within the program. If you're willing to do some reading, you can usually figure out what you got to do. Okay, as far as EAGLE, the documentation on the LTSpice UOP itself is actually pretty sparse. It's going to be over here in LTSpice UOP. If you actually click on it, this is all the documentation on the LTSpice UOP. Everything that was written to document this UOP is here. Okay, I've actually taken the liberty of copying that and printing that out for my own use. So if LTSpice is something you guys are going to be working with a lot with EAGLE, definitely recommend printing this out, and it'll come in handy. There's a couple of points we'll go over as we go through the demo, but this is basically the extent of the documentation that LTSpice has made for it. Okay. Additionally, within EAGLE, just want to highlight you have the Help, which covers all the commands, all the syntax, and you have the manual. Okay, which under the newest version of EAGLE, I'm using 7.3.2 beta right now, will show up under the documentation tree. Okay, so you have all the manuals, all the tutorials. The key document to know here is the manual, okay, and the Help. There's actually very little overlap between the two. So if you don't find something in the Help, you'll find it in the manual. If you can't find something in the manual, you'll find that in the Help. Okay, so that's what I wanted to start off with today. Now, let's go ahead. Let me close this. Let's go ahead and get started. The first things I want to walk you guys through is the basic usage of the LTSpice EAGLE bridge. Okay, so I'm going to go ahead and open up the schematic here. Okay, and you're going to notice these are pretty much using symbols that are in EAGLE's library. Okay, pretty straightforward. You'll notice these voltage sources here. These are simulation sources. Okay, normally you would have some sort of linear regulator, or the reality would be a linear regulator or switch mode regulator. Okay, and this brings us to a first key point about simulation. It's generally very difficult to simulate the entirety of a circuit. What you want to focus on is the key points you want to make sure are plausible, or the design elements you're not 100% sure about. That's where you really want to focus your simulation effort. So things like, the power rails can be substituted with this simplification, which is a voltage source. Okay. So the LTSpice UOP is controlled here through Windows, through this little button up here in the dialog. I want to make the point right now. Currently, the LTSpice UOP is only set up for Windows. It's not available for Mac or Linux yet. That's something I'm working on to get that resolved. And it's actually nothing that has to do with LTSpice itself. LTSpice can run on Linux or on Mac under the Wine emulator. I believe that actually under Mac there's some unofficial version of LTSpice. What ends up happening, and we're going to get to that now, why it doesn't work under Mac or Linux at this point in time. Okay. So the first thing you want to do whenever you're going to do a simulation, we go to Export Setup. Okay, it finds library. Okay, we say okay, cancel. Now we're over here. Okay, this is the auto setup info. Okay, and the goal here is it figures out what version of EAGLE you're using, what operating system you're under, the path to the EAGLE executable, the path for the program itself, user directory, where the executable for LTSpice is at, its library directory, etc., etc., etc. This right here is what currently makes LTSpice, the UOP, not compatible under the Mac or Linux operating system. All of these paths are hard-coded into the UOP. Okay, so if you alter where you're installing LTSpice or you make any other variation on that, then the UOP won't be able to find it. Okay, and that makes this setup a little fragile. If things aren't set up in a way that the UOP expects, then none of the interface can work. Okay, so the ideal situation, or what I'm shooting for to do with this, is to, on the Linux and Mac systems, is to basically allow the user to define these. Okay, and if once it goes through the hard-coded path, if it still can't find it, even on Windows, let the user define where these locations are at. Okay, so right now, this is defined here. And I'm going to show you guys a little trick later to be able to see how you can change these by going into the code. But for now, the setup is happy. We did it. And now what we can do is we can go File, Export, and it goes straight into LTSpice. So what you guys can notice immediately is if everything is set up properly, the process is flawless. The process is very easy, very straightforward. Okay. As you can see, we have the SPICE directive here for what's being analyzed. Okay. This is going to be a transient analysis for 1 millisecond at startup. So all I'm going to do is just run the simulation. Okay, and we can start probing different parts of the circuit. One of the more interesting parts is the inductor current. Okay, so I'm going to go ahead and let that run. You guys see how it starts up. Okay. Now we can also check out here. I want to point this out to you guys over here. This is a switching MOSFET, okay, that drives this entire setup over here. Okay. If we look, I'm sorry, not the switching MOSFET. That's to allow power to go through. I stand corrected on that. Switching node is here. Okay, here we can see the switching frequencies. So let me go ahead and zoom in on this. And we can see how the switch mode power supply, which is what this is, okay, starts up, the duty cycle gets adjusted, and as we work our way across, zoom out, okay, we see how the duty cycle starts to adjust to keep that current increasing up until we get to the point for the current that we want to have here, up to our steady state current. Okay, so now the duty cycle has stabilized. That's our ripple, our current ripple. Now we can see that it's pretty accurately modeled how this part behaves in this regard. Okay. Now again, in the case of this part, this is an LT part, so they've gone through every effort to really try to model as much of it as they can, all the different parameters, how it behaves, etc. Okay. So not all models are that complete. For example, not all op-amp models will cover every little facet of the op-amp you're working with. Sometimes input bias currents are difficult to model, the input impedance, because it's often not purely resistive, but rather reactive in some way. And many other slew rate is difficult to model, so on and so forth. So depending on your model, certain effects may not be observed, and those may be critical to your application. Okay, so again, I keep emphasizing this. Don't look at the simulator as a source of truth. You need to have some idea of what you expect the output to be. And then when you run the simulation, you can say, okay, so it looks like I expect it to be. That gives you confidence. If it looks completely off or completely different, you need to figure out why. Okay, so either way, the simulator serves as a sanity check. So that's the simplest use of the LTSpice simulator, going from EAGLE to LTSpice. Now the reverse is also true. We can go from LTSpice into EAGLE, which is what we're going to do now. I'm going to go over here. Port. Oh, it wants me to close LTSpice because it opened it. Go ahead and close it. That's another issue with the bridge. The UOPs are blocking. So as soon as it calls something, as soon as it calls an external program, the UOP will be on hold waiting for that external program to close before it'll let EAGLE continue to work. So keep that in mind. The call is blocking, something we're looking to improve with UOPs. So let's go ahead and pick something interesting to import. I'd like to go ahead and import this band gap over here. Let's do that. Let's do that. Okay, band gap schematic. C equals 7.3.2. Let's put it in there. Say OK. A device not found. A, B. Okay. So what can happen? Those errors that we saw before, those are usually labels. Okay, which are missing now in the design here. Okay, so you guys can see the different band gap references. Normally there would be labels here at different points. As you can see, it came in pretty much perfect as the resistances, has different transistors. We can go the other way. We can, for example, export just a group. So let's go ahead and select this group here. File export group. There we are. We're back at LTSpice. The group's been exported. Okay. So as you can see, when everything is set up properly, things go by very, very smoothly. Okay. And I keep coming back to this point of setup. Setup is the key here. Okay. Using the LTSpice EAGLE bridge is very front heavy, very front loaded. You have to make sure there's correspondence. Okay. And this is the key point here. Correspondence between EAGLE's library and LTSpice library. Any parts that you have in your EAGLE schematic, any models that you have, okay, need to have a counterpart in the LTSpice libraries, okay? So any part you use in your design, there must be a counterpart in the LTSpice libraries. Likewise, to bring in something from LTSpice into EAGLE, there needs to be a counterpart. So the key here is always making sure that for whatever you're using within EAGLE, there's an equivalence in LTSpice. If you started in LTSpice and you want to import into EAGLE, there needs to be an equivalence. Okay? Without that, you'll find that it's difficult or near impossible to get anything to import. But luckily, the designer of this interface added some provisions to really simplify achieving that correspondence. Okay? And that's what we're going to go into now. So that's the basic functionality of the LTSpice bridge. Okay, as you can see, these 4 options here. So let's go ahead and open another design. No, don't save it. That's going to be our demo for today. So open this up. Now, a couple of things I want you guys to notice, okay? You guys can see the purple text here. Okay, notice how all of the parts that are going to be simulated have that purple text. When you're making your circuits, okay, in EAGLE, in this case, this is strictly a simulation schematic. There's nothing here physical. But your physical components, devices that you're using, they can be mapped to LTSpice models. Okay, so like this op amp has packages that go with it. In this case, I have a dual inline 8. Okay, so this is a full component. It has a dual inline 8-pin package. Now, if any of you are familiar with the LM741, there's pins missing on this model. Okay. Right now, all I have is the non-inverting input, the inverting input, negative power supply, positive power supply, and the output. Okay. Let me very quickly go ahead and look up LM741 datasheet. And if you guys look, there's actually additional signals in the real part, which are the nulls. Okay, the ability to offset to 0 the part. Okay, our model here in EAGLE does not include those nulls. Okay, and the reason being is that the SPICE model I was able to obtain for the LM741 doesn't take that into account. So right there we have one deviation from reality. Okay, for this application it doesn't matter, but maybe for another it does. Maybe I need to be able to simulate the effect of the null on the LM741. With this model I can't do it. Okay, so it's very, very vital and important that you're aware of what your models cover, what their capabilities are, etc. Okay. Now, speaking of models, where can we obtain models? Okay. Most manufacturers willingly give them away. It's obviously in their best interest that users, customers use their parts, so they give you all the information necessary to make it easy to use the part. So, taking as an example TI. When you visit the Texas Instrument website, if you go Tools and Software, immediately under Analog Design Tools, you're going to see SPICE Models and Libraries. So click there, takes you to this page over here. Okay, and they have models for different programs: PSpice, TINA TI, HSpice, and they have generic SPICE models. Obviously, TI is not linear technology, so they haven't tailored any of their models for LTSpice, because LTSpice is a competitor. It's made by Linear Tech. So you want to use the general SPICE models for this. Okay? You can download them and save them and have them ready for whenever you're going to, do some simulation. Okay? So right now, let me see if there's any questions. Anything pending? So far, so good. Okay. So right now, what we're going to do is we're going to go ahead to this new design that I have here. And those who have seen the other webinar that I did on the LTSpice interface are going to recognize this. This is the same design I used back then. Okay? So what we're going to do now is we're going to go ahead and I'm going to try to export it just off the bat. I made my part. I'm ready to get this going. And I want to simulate. And I go File, Export, and I get this message: C programs symbol does not exist as an LTSpice symbol. Open the library and device and export the device and symbols. Okay, so this is error number 1. Okay, and this particular error is letting you know that there's no correspondence. Okay, in LTSpice, I don't find this symbol, therefore I can't do anything with it. So we say OK, and it wants me to open the library now. Okay, this is the library I made for this. Now I have it open. Okay, so as you can see, I've made this component very happily. Okay, I have my packages. I have 2 of them. I've done the mapping to the best that I can because I don't have any nulls on this thing. Okay, it's a limitation of my simulator. Ideally, to make everything as accurate as I could and to reflect, some of the connections I may want to make on my board design, I would try to seek out a better model, or I would do this as a separate thing. Basically, just use this schematic as a simulation schematic, and then lay out the full thing later with a full device ready to go. So prefix, this stuff is normal for you guys. Okay. Now, how did I get to making this part? Okay. The package part, if you're familiar with EAGLE, that's pretty straightforward. That's no different when we're doing an LTSpice component. What is different is it's all in the symbol. All the magic happens in the symbol. Let's go ahead and open our symbol. Okay. So the symbol is drawn normally. I put in my pins normally. I can use the info command to check on the pins, sorry. Okay, these are all the normal pin parameters, the length, etc., etc., etc. Okay, nothing out of the ordinary there. Now these texts here, spice order 2, what the heck are those, right? That's the question. How did they get here? Okay, the LTSpice utility gives us the spice order UOP that comes with EAGLE. Okay, so we click on spice order, and basically these texts come from the definition here in spice order. Now, what is a spice order? What does this mean? Let me show you guys. Okay, I have this is a text editor I like to work with, Genie. I'm going to go File, Open, and EAGLE Spice Demo. I'm going to go ahead and open up this sub here. Okay, originally it was mod. I just changed the extension to sub. Okay, I hit Open. Okay, and this is the model. This is the entirety of the spice model. And as you guys can see, this kind of looks, I wouldn't say code, but it kind of reminds you a little bit of code. Okay, the spice language is a language of its own, developed in the 80s for the simulation of analog circuits. It's very old, but still one of the most reliable and flexible simulation frameworks. Hence, everybody uses it. Okay, that's why you can see that even though I got this model from TI, I can use it in LTSpice because it's a generic standard language. Okay, the models that are tailored for other programs, PSpice, so on and so forth, those models can leverage certain features specific to those simulators. But it's nothing beyond the normal LTSpice language, the normal spice language. Okay. Now the spice order is actually defined here. Okay. In this line. Here's how this works, guys. Okay. The model of the LM741 is made up of a whole bunch of other components: resistors, transistors, capacitors, etc. Same way as we saw here in this document. Okay, these are standard spice objects. These current sources, resistors, these are very standard spice objects. So when you build up a model of a component, you can use those base component parts to build up the model, and that's what was done here. Hence why it gets the sub-circuit directive. Okay. Now what are these numbers? These numbers here point to nodes in the model. Okay. So for example, 50, the negative power supply, we see it referenced over here. Okay, with source I1 connecting between node 4 and node 50. Okay, that's what these represent. And if we look carefully, we can find them all. Because this text defines all of these objects. Now, these numbers here, like I mentioned, are node numbers. They have nothing to do with spice order, which is what we're interested in for our part in the library, right, to define this order. The spice order very simply is going from left to right in increasing numbers. So this right here, this pin, is spice order 1. This is spice order 2, spice order, let me just highlight it, spice order 1, spice order 2, spice order 3, spice order 4, spice order 5. Okay? Those are our 5 pins. So we look at this, non-inverting in, graciously, TI documented this well. Not all models are this well documented, okay, just so you know. But they've documented this well, and it's here. Okay? So, we got this going. This part's all right. Let's go ahead now and go over here to our library. I go to Spice Order. And what we should notice is that our non-inverting input, that's spice order 1. Non-inverting input, spice order 1. Inverting input, spice order 2. Inverting input, spice order 2. Positive power supply, B+, spice order, output is spice order 5. Here's our output, the last one here. Positive power supply, spice order 3. Here we are. Negative power supply, spice order 4. Okay? So hopefully that makes sense. That's pretty straightforward. Okay? There's no requirement that a SPICE file needs to only have one component, one main model. They can actually be collections of models, and they're all, each individual part will be defined by this sub-circuit entry here. And there may be a few other small ones here defined. No, that's it. Okay. Cool. And if you guys look here, these are built-in models of the SPICE language. This is a diode. This is a transistor. And you can put in extra parameters to help make the analysis more accurate. Okay, any questions thus far on this, on the specific SPICE model and the SPICE order situation? Okay, this is a very key point to making your own parts to work with the LTSpice interface. Okay. So now we've got the SPICE order thing set up and cleared up. Okay, we're going to go ahead and go to the device. Now in the device, under LTSpice, we're going to notice that we have some extra things. Okay, we have value 2. Value 2 should generally be set up to be the same name as the device. That's a recommendation as given in the documentation. That's specifically in the creating new symbol section. Okay, in under frequently asked questions, that creating new symbol section, that covers this. Okay. So we have that. That part's okay. The other thing we want to make sure we check on is the SPICE model. Okay. In my case, LM741.sub is the model I'm going to be using. We can see that from the EAGLE control panel. Well, let me okay this. Go to the EAGLE control panel. I already have an LM741.sub. Okay. So we've already assigned all the parameters here. We have our SPICE model, our SPICE order set up, value 2. Okay, this part now exists in EAGLE, but doesn't exist in LTSpice. We need to make it exist in LTSpice. So we can do this by, again, clicking on the LTSpice, and we go export. Okay, it's going to export the symbol, and it's going to export some additional information. We can say to export everything in the library or just this device set. Okay, we want to export just this device set, so we'll say OK. And that's it. Device set exported to, so it's already saved it. It's already saved that model to the appropriate folder within LTSpice. Okay. So now if we go over here, okay, we go export now. That worked. Okay. Now I have this include directive. It's not going to be necessary because if I recall correctly, if I set this up right, this should fail. If it doesn't, that means I left the model when I wasn't supposed to. So I go to run, and it worked. So it looks like I left the model where I wasn't expecting to leave it. Okay, but as you can see, it took care of it. I could actually remove this include line. It'll be okay. Go ahead and actually I'll comment it out is what I'll do. Put it as a comment. Okay, it's not doing anything now. Okay. If for some reason this point doesn't work, guys, if this should fail, then a couple of things you may want to try. Okay. One thing you can try is copying going to try is going to copying this .sub model. You just do a file copy. We go to C, program files x86, LTC, which is LTSpice, lib, and the sub. And we go in here, or we can just paste it into here. And you can see these are all the models for all of the components LTSpice ships with. Okay, and as you can see, they're all LT components. Okay, so keep that in mind, guys. So we can go ahead and do a paste, and we include the LM741 in there. Okay, if you should have any trouble getting that to work. If that still doesn't work, then this statement here can take care of it for you. Okay, .include LM741.sub. Make sure it's in as a spice directive. Okay, spice include directive. If you were to have a library that contains multiple symbols, then this would be, ti.lib, for example. Okay, and you can include that just to make sure LTSpice can find the model. So this is ready to go, and we can simulate. This is a very simple little transient analysis. Okay, we have the sine wave input, and we have the output. And if we zoom in, we see that we get our expected result of a gain of 10. This is a LM741 in a non-inverting configuration, so it's designed to have a gain of 10, and that's what we got. We got a gain of 10. Okay, perfect. Everything is working as we expect it to. Let's try a different simulation here. Okay, we want to do AC analysis. Okay, I'm going to do octave, and let's do a start frequency, I don't know, do 10 hertz to, we can do, I don't know, let's see if I got this right, 1 gigahertz. Let's just see what happens with that. We'll want to change this. I do this as an AC source here. So the AC amplitude is going to be 0.1. The phase 0. Got this. Go ahead and do the simulation. Okay, from 10 hertz to 1 gigahertz. Okay. Now, what was my point behind doing this simulation? Okay, I want to show you the accuracy of this LM741 model. Okay, an ideal op-amp model, as many of you will know, doesn't take into account frequency limitations of the component. So if we were using an ideal op-amp model, what we would see is just a straight line going across. Okay, with no drop in gain, no adjustment, no change, nothing. Okay. You see no change there. And let me add to this plot. This is fine. This is fine for the purposes of the plot. I'm going to go ahead, and you can see that this model takes into account the inner poles of the op-amp, and in fact, it takes into account 2 poles, because we see one rolling off over here, and then the gain, the slope changes, and then it just becomes crazy after that. And then all the capacitive impedances, basically you get resonance over here, and then this is dead after this. It's completely unusable. Even here, we're starting to lose gain accuracy. Okay, so this is an example of a good model that TI has provided for the LM741 op-amp. They're not all going to be this good. Okay, so you want to make sure you know the limitations of the model. Okay. So that pretty much covers that. Let me show you guys what the LTSpice model looks internally, what the UOP generates. Okay. To show you now a couple of more details. You can see that I have my spinning mouse cursor. EAGLE right now is blocked because the UOP called LTSpice. You can see it here, running LTSpice at UOP, waiting for return of SCAD3.exe. Okay, until I close LTSpice, it's going to be very difficult to do other things within EAGLE. EAGLE's completely blocked. We can do nothing else. Go over here, and we close EAGLE. LTSpice. So we say no, we don't want to save it. No, okay, good. Okay, so now we're back. Now things in EAGLE should work. So keep that in mind. This line, this value line I got, that comes from basically following the same syntax as LTSpice would follow. Same thing when here. If you guys look over here, these lines of text, the way LTSpice interprets some text as a spice command is by us putting, basically escaping the exclamation point. If you do that, it'll interpret it as being a directive, a spice directive, okay? You okay on that? Go back to the control panel. And this is our design. This is the converted design. And if I just open this in EAGLE's text editor, you guys will see that it's actually pretty straightforward. Okay? It's a very simple format. It's completely text-based. So if you like to do programming, you can actually manipulate this outside of EAGLE, outside of LTSpice. I've actually seen guys put this text, design a circuit in LTSpice, grab this text, copy it into something like Excel, and have Excel calculate values for components, and then basically use Excel to design a circuit. It's actually a pretty interesting exercise to do whenever you guys have a chance. But as you can see, nothing crazy going on here, nothing too difficult to do, even by hand to develop. Okay? Now, as far as the fragility of the LTSpice UOP, remember how I mentioned that the paths are hard-coded into it. I'm going to go ahead and use my Genie editor again. Go open. This time, I'm going to go into C. There's a whole bunch. Spice UOP. Oh. And this is, for all practical purposes, the entirety of the LTSpice EAGLE bridge. Okay? It's about 2,000 lines of code, if memory serves. I stand corrected. 4,500 lines of code. Okay? And you can see it's pretty heavy duty. Where the fragility comes from is actually near the end. Hopefully I don't miss it. That way, if you guys have any issues on Windows, I mean, it's not reasonable for me to expect you guys to keep this, you know, perfectly memorized and in the back of your heads. But I do want to show you that if you are having issues getting the interface to work, how you can control the paths. Okay. So let me go ahead and prefix, technology. Bear with me 1 second. I really just want to make sure I don't miss this. So the import functions. Fine. Export setup. Here we go. Here we start getting to. Okay, here we go. Here we are. Okay, so if you look here, these are, and this is in line 4,145. Okay. So when you guys run the export setup, what it's basically doing is it's checking these directories, which are hard-coded into EAGLE, into the LTSpice ULP. These are hard-coded in, looking for this. Okay. If it can't find it, then that's where you get that issue. Okay, LTSpice not found, and you have to OK, and then you have to go figure out where it is. The same thing will start to happen with the other directories. Okay, and you'll see that it'll, once it finds this key one, then the other one's kind of set up pretty easily. Okay, so if you've installed LTSpice somewhere else, all you have to do is add that root path in here somewhere. Okay, basically as another option. I encourage you not to remove any of the old ones. Okay, just tack on another one at the end. When you run the setup, it'll grab it. It'll find it. Okay. Is there any questions you guys have for me on the interface now? Anything that bugs you? Anything that wasn't clear? I know this was a lot of information to cover, so please feel free to send in any questions, any concerns. This pretty much covers what I intended to cover for this webinar. If there's anything you guys feel I missed, or anything you'd like to ask me, please feel free to enter it now. Okay. So I guess you'd be really happy. No questions. If there's anything, guys, feel free to let me know. You can always contact us, support at cadsoftusa.com. You'll usually be talking to me. You can also call us, 954-237-0932. Okay, so 954-237-0932. Let me make sure there was nothing else I wanted to tell you guys. Oh, LTSpice isn't the only bridge we have in EAGLE for simulation. Next month, we're going to be doing a webinar about PCB sim. Okay? I was getting a PCB sim. Okay. So we invite you guys to attend that one so you can see the other option that's available for simulation in EAGLE. And then I have a question here from an agenda. You were getting a can't build error. Agenda, the only thing I can say is probably maybe after this webinar, shoot me an email, support at cadsoftusa.com. Include the files in question, and let me have a look at it, and I'll see if I'll figure out what's going on, and I'll let you know why you're getting that error. Okay. Keep in mind, it only works right now under a Windows operating system. Okay. Any other questions, guys? Anything you liked, anything you didn't like, suggestions, you hate my guts, I'm totally open to any criticism. So let me know. Okay, I'll give like 2 minutes for any other questions, and then we'll just call it a day. Okay, the phone number again is 954-237-0932. Actually, what I'll do is I'll send everything to the chat to everyone. That way everyone has it. Okay? Or to cadsoftusa.com. And here's our number, 954-237-0932. excellent question. What about the possibility of IBIS simulations? Awesome. So in the case of LTSpice, LTSpice is strictly an analog simulator. It doesn't handle the signal integrity stuff. Let me rephrase that. It doesn't handle the signal integrity stuff easily. It cannot handle an IBIS model. You can do some signal integrity by simulating transmission lines and stuff, but then the program we're going to analyze next month, PCB Sim, that one can do full-blown IBIS simulations. It will also do S-parameter simulations, and on top of that, it can do SPICE simulations. So the one next month is actually a pretty heavy-duty program, and the interface is different than the interface with EAGLE that LTSpice has with EAGLE. So we'll check that out next month, and I'm sure you guys will find it very, very interesting. Okay. Okay, so guys, if there's no further questions, I thank you all for your time today. Feel free to send any comments, anything you guys need to support at cadstufusa.com or the number. Like I said, this has been recorded, so I will be posting the link on the webinar page so you guys can download it at your own leisure. We're working on getting these up on YouTube. They're not up yet. I've been converting all of them to MP4s. Once I have everything set up, you'll be seeing the last few webinars also come up on YouTube. Okay? So thanks, everybody. Have a great day. If there's any further questions, like I said, feel free to contact us. Thank you for your time.